Hello. Today we're going to be going over problems 11.3 and 11.4. So in 11.3 that is on the screen currently, the problem analyzes the temperature control loop for a stirred tank, and then the main goal is to determine how well the system tracks the set point. And then first the transmitter spin converts temperature to MA signal, which gives the measurement gain Km. Then all components in the loop are multiplied together to form the overall loop gain, including the controller gain Kc, current to pressure converter gain Kip, valve gain Kv, and process gain K2. The transfer function shows how the output temperature responds to a change in set point. And then using the final value theorem, we evaluate steady state behavior to determine the offset between the set point temperature and the actual temperature. The offset temperature occurs because proportional control alone cannot eliminate the steady state error. And then finally, we solved for the process gain K2 that produces the observed steady state temperature difference, and then we calculate the pressure signal required at the valve to maintain the final operating temperature. And then for problem 11.4, which I'll scroll down so you can see all of. The problem goes over a mixed dynamic model. The first step was just writing the total mass balance and the solute balance on the tank. And then the outlet concentration equals the tank concentration because it's perfectly mixed. And then the dynamic equation shows that the rate of change of the concentration depends on inlet flow rates and concentrations minus the outlet flow rate effect. The equation is then linearized around the steady state operating point, so it can be written as a transfer function. And then from this, identified the process gain and time constant, which describe how quickly concentrations respond to changes in flow rate. And then the block flow diagram is constructed by linking each element, transmitter, controller, valve, and process dynamics. Finally, we went and evaluated whether the controller needs retuning when operating conditions change, if concentration span or flow relationships change, gains in the loop change, so the controller should be retuned. However, if only the transmitter zero shifts but the span remains constant, the dynamic response of the loop does not need to change. So it is not necessary for that final one.